So practice exam, going through some of these. First one, these are nomenclature ones. So again, definitely going to have an alkene one and going to have an alkyne one. So hex means 6. So 1, 2, 3, 4, 5, 6. So you got there. 5 ein, right? So 1, 2, 3, 4, 5 ein, 2, 4 dimethyl. And the biggest thing to remember too is to not have your bond angles be correct. That's one thing. This is a diene, pentadiene, 1, 2, 3, 4, 5. 1 and 4 means that's where each alkene starts. So carbon 1 and carbon 4, and then 3 methyl right there. So number 2, draw the mechanism. Again, these are the kind of problems that said we were going to have where you were given the starting material, the reactants, and the product. You draw the mechanism, give it all 3. So if you can see here, if you did some numbering, perhaps, you would recognize 1, 2, and then it looks like 1, 2. Right, I'm not going to try to do any tricks, move things around on you. It looks like there's been a rearrangement, which should, in your head, say, oh, then I must have a carbocation. So for this one, this is like a hydro, essentially like an acid catalyzed solvent, protic solvent addition. So H plus is the catalyst, protic solvent on the bottom. Pi bond reacts. You put the H on the least substituted carbon, so you get the more substituted carbocation. So this is a secondary carbocation. If you have a secondary carbocation, try to make it more stable. You can do an alkyl shift, the carbon shift there, and that's going to move that there. Again, being careful, the whole atom moves with it. Now you got a tertiary carbocation. More stable, can't make it any more stable than that in this case. There's no pi bonds or lone pairs. Now the solvent reacts. So the solvent adds, it can have from the top or the bottom. You always will have a plus charge on the solvent when it adds. Don't shortcut any steps, right? The H's are still there. These 2 carbons are still there. H just falls off. That's the catalyst part. And then you ask yourself, did I make an asymmetric center? You actually didn't here because there's 2 methyls, so you don't need to worry about wedges and hatches. But with carbocations, you'd make both if you made an asymmetric center. So more like a fill in the arrows, but also number all the carbons and add lone pairs on all oxygens, right? So don't make sure you follow directions really explicitly. So make sure you numbered all the carbons and not just on the starting materials all the way through. So make sure you did that to see where everything ends up at. And add lone pairs on all the oxygens, so make sure you did that as well. 2 arrows this first step makes that 3-membered ring. Common mistakes people make, they forget the second arrow. Or on this one, when the solvent reacts, right, it goes to the more substituted side because it's Markovnikov addition, and it's a trans addition. But this lone pair needs to go to carbon 2 in this case, not carbon 1, and you need to show this bond breaking, right? Again, just tracking where things go. You see the water and the mercury now trans to each other, so you have a tautomerization, and then you get to this mercury species where the mercury just falls off, right? Mercury's like a big hydrogen, so the electrons go there to make a new pi bond, and the pi bond breaks, electrons go to the oxygen to make another enol, which then undergoes a tautomerization with acid catalyst. Acid, you can do it this way, and then finally the H just falls off, and you get the ketone for this one. But again, number all your carbons, add the lone pairs and all the oxygens, and just really focus on where the bonds are broken, bonds are formed at. So some multiple choice problems. They're kind of fill in the blank. So you see O3. You got to recognize that's the one where you take an ozonolysis, where you take an alkene or alkyne and kind of like scissors down the middle, and you make carbonyls on either side, acetyl bond O's. So in this case, you have 2 ketones, so that means it's sort of an alkene. If it was carboxylic acids, you'd know it was an alkyne. So because it's an alkene, just doing some numbering here, 1, 2, 3, 4, 5, 6. So I should recognize that 1 and 6 are forming the pi bond, right? And I see that 1 is still bonded to the ethyl, and then 6 is bonded to the methyl here, and 2 had a methyl, and I just kind of pinch it back together, piece it back together, then go look for my answer, and it's actually this one, just to rotate it around. But yeah, numbering your carbons here is really important. All right. So product of the first step. So this is just seeing, right, when we do a hydroboration, there's a syn addition where the boron and an H add on the same side. And the boron goes to the less substituted carbon of the alkene or alkyne. And the other part here, the other answer some folks might have tried to do, well, let's see, this is on the first step, right? I bolded that. And then make sure your ethyl and this H, there's an H here. Right? Always draw in the H's on the alkenes or alkynes. That ethyl and this H are on the same side, and these two methyls are on the same side. Right? So boron adds syn. Boron goes to less substituted carbon. Here they're adding trans. Here's it on the wrong way. And here's after the second step. For this one, why does the reaction give the Markovnikov product? This is all about the carbocation stability. Right? So if you did the first step, right, you'd have this, and so why does this form versus this? So this is a primary carbocation, and this is a tertiary one. So the reason the tertiary one forms is because it has more sigma hyperconjugation buddies. Sigma bonds 3 bonds away. So this has 9, this has 3, so it's because of hyperconjugation that you get the Markovnikov product, which just means the thing adds to the more substituted side. It's another alkene one. What's the product of the reaction below? Got to recognize this is halogenation, and also recognize this is solvent, but it's not a polar protic solvent. It's aprotic because there's no OH, NH, SH, or CH. So in that case, what are you going to do? This has nothing to do with anything. So it's just halogenation. You're going to add bromine twice. Don't need the mechanism. You just got to remember the bromine adds trans. So it's the only one of the bromines are trans. Bromines are syn, bromine and H, and solvent, so it's just this one. So just going through the mechanism quick here. So first 3 arrows, pi bond reacts, reacts with the first bromine. Bromine bond breaks. The first bromine comes back around, makes a 3-membered ring, a bromonium ion. Since we have a polar aprotic solvent, the solvent doesn't do anything. It's just Br minus that's involved. And now we have a choice to make. Carbon 1 and carbon 2, which one's more substituted? That's the one we want to go for, is the more substituted carbon. So in this case, that'd be carbon 1. And it's always going to be a trans type addition. But it's always going to go for the more substituted carbon. And that's what's going to give you this trans bromine product. If it was protic solvent, it would also go for the same carbon, doesn't matter. But it's always going to go for the more substituted carbon. So give the mechanism for the reaction below. Again, you're given the starting material, the reagents, and the product. Ask to draw the mechanism. You need to recognize here, that's a carbon, that's a lithium, that's actually an ionic bond, right? It's not a regular covalent bond. So this is also similar to Na plus NH2 minus. Same idea, really reactive, strong base. So you're going to do double elimination, which you could recognize by saying 2 pi bonds when there was no pi bonds before. So you're going to do first elimination. It needs to be anti-periplanar, but it doesn't matter in this case because there's no wedges and hatches or rings. The second one, though, so you do your E2, 1 step, 3 arrows. You're going to do 2 of those. And your second one, 1, 2, 3, 4, 1, 2, 3, 4. You should draw it like this so it's anti-periplanar for the second one. So you're setting it up to look like this. So the H and the bromine are 180 degrees apart. Just do an E2 again, and that gets you to an alkyne. This one, just matching, right? You just got. I remember these are the 3 of the reactions I just told you had to kind of just know. Transalkene, that's the lithium dot or sodium dot. So it's not the plus, there's an electron there, it's the metal, and then this is the solvent. C was all the way from alkyne to alkane, right? So you add 4 hydrogens. So this is C, that's palladium on carbon, the same one you use for alkenes to alkanes. And then for this one, B, it's that Lindlar's catalyst where you take an alkyne and make an alkene, but it's a cis addition. So you add the 2 H's, cis versus trans, or all the way to alkane. All right, now it's like the 3 different ways to do tautomerization. Different years, I emphasize different things. Always definitely do the neutral version where the pi bond takes the H. Make sure you're doing the right direction. Pi bond's the nucleophile. Pi bond's going to go get an H. Think about you're trying to add an H to this position right here. So the pi bond always goes and gets an H for all of these. Right, at the end of the day, pi bond goes and gets an H. These 2 electrons here form that new pi bond. So this is under neutral conditions. Here's tautomerization under acidic conditions. So that means the pi bond goes and gets the H, but the H is now the catalyst. So the electrons come down, make a pi bond, and then the H falls off, or you could have the H fall off all in one step. It's up to you. Get to the same thing here. Base catalyzed, a little different. The base now deprotonates the hydrogen, takes the hydrogen off, makes an O-. It's called an enolate. Learn more about those later. Electrons come down, pi bond reacts. You remake OH-, which is the catalyst, which you need to do. Get to the same tautomerization product. We did some reduction ones. Now these are the oxidation ones. Some years I have them do the mechanism. Sometimes I don't. You all could do these. If you're given this, you could in the product. You can always draw in the arrows for anything really. Just think about what bonds need broken and formed. But for this, for sure, if you see this and you see O3, that's that cutting this in half type thing, where you make 2 carbonyls on either side. So this way you make 2 aldehydes. And depending on depending on years, different reagents can give carboxylic acids too, but we kind of focused on these ones this year. This is a peracid. And peracids make epoxides from alkenes. So we talked about that. Maybe not. Sometimes we talk about mechanism, sometimes we don't. This is osmium OSO4. And we talked about this. Actually, the next part here it makes a syn addition of hydroxys. It's a dihydroxylation. So the final product is a syn addition of 2 OHs. So different years, different times. I focus on mechanisms. Sometimes I do, sometimes I don't. For sure, always want people to know, right? Recognize the reagents and the starting material, and then what the product would be. Reagents, starting material, what's the product, or vice versa. 2 out of 3 you should figure it out. There you go. All right, so give the mechanism and the product for the reaction below. So this one I give you the final product, and I'm kind of asking for the intermediate. Br2, so you're going to have 3 arrows because you're making 3 member ring with bromine. This is an alkyne, so we should number our alkyne carbons. Notice the bond angles are correct here. Don't get goofy on your bond angles. Also notice we have 3 arrows, just like we've seen. We have a polar protic solvent, so that means the solvent's going to be involved. OH, NH, SH, or pH. So the solvent's going to be involved. It's going to go for the more substituted carbon. So that'd be carbon 1 in this case, as I have numbered it. That has nothing to do with naming. So it's going to add there the more substituted, break that bond. The H could just fall off, or the bromine could get it. It doesn't matter, right? Then you get this enol, right? You get this enol, which then is going to react with Cl2, right? So now it's an alkene, and it's going to do this, make this ring with chlorine, and now the solvent here now is methanol, so it's still a protic solvent. Again, we're going to go for the more substituted carbon, which is still carbon 1, but we're going to get that trans addition again. Right, so the methanol and the chlorine are trans. Just like before, the OH and the bromine are still trans. See how they're wedged? This is wedged, that's hatched, they're trans still. And that gets us to our final product. A couple things people will forget to do. The 3rd arrow for both of these. And they'll not draw their arrows to the carbon, right, that the solvent is supposed to be adding to, the more substituted one. Or they'll forget to break this arrow, this bond right here. They'll try to break this one for some reason sometimes. But yeah, balancing your charges, slowing down, right? It's just falling off, all that kind of good stuff. Number your atoms. That's the key. So 13. So this is one of those ones where you're giving a starter material and then a product. And just because I have 3 arrows here doesn't mean there's 3 steps. I guess it ends up being 3 steps here, but that's not meant to signify 3 steps. It's meant to signify multiple steps. But I guess people saw it as 3 steps. Things I did, I numbered the carbons in the starting material and the product so you could see them. Things you should notice, right? These are one of those problems we talked about, right? What has changed, right? Looks like we've added, right? Add 3 C's, right? Oh, we added 3 carbons. Well, there's only one way I know how to do that. That's going to involve, right, Na plus and H2 minus, right? Or that butyl lithium. I need to add 3 carbons, and it looks like it's this piece. So maybe we need something that looks like this, because the carbon I need to add right there needs to be attached to a leaving group, because I want to make carbon 3 a nucleophile, because it's a terminal alkyne. There's an H there, right? So these are all the kind of things you can look at and know and just write down to earn some points. Now, working backwards, you see the 2 chlorines are trans, the 2 H's got added there. You want to add the H's last. So the chlorines are trans. One step back would be an alkyne where the chlorines are trans, right? You probably wouldn't also want to say here, right? It'd be important to say 1 equivalent too, right? Because you only want to add 2 chlorines, right? If you said excess, you'd add 4. From this alkyne, you can see, right, there's the bond, right, that was going to be between 3 and our electrophile we're adding, right? So to do that, we have to use this piece. First, we deprotonate, then we add this piece, then it goes. Then we do Cl2 when equivalent, H2 plate on carbon, syn addition, and everything matters. There has to be this correct order. So these problems are hard. I'm not gonna say they're not, but I'm not asking for the mechanism. So don't give me stuff I don't need or don't want, and write down, right, some notes about what you're thinking and trying to do, right? Like you can say I need to add these H's syn. I forgot the metal, right? I mean, there's different things you can do to say show what you're thinking for these kind of problems. So what am I actually asking you to do here, right? I'm asking you to come up with a set of reactions to go from here to here, right? So I'm saying you can do anything you want to go from here to here of what you know, right? So you can look at this and say, okay, I need to add 3 carbons, I need to add H's syn, I need to add chlorines trans. Like you can just write that down right away, and that'll get you about half the points for this problem. Just like recognizing what's happening, right? And then you got to go and say, okay, how would I actually do this? Like, do I know the reagents to go from here to here, which I need, and then I need to take this and do this and then that, right? Like, so it's you making it up on your own, what you need to do and the order you need to do it in. So just like strategically thinking about this, right? You need to put the carbons on at the beginning, because that's when you have an alkyne, a terminal alkyne. That's when you have to put the carbons on. It's like the first step, right? And if you notice, you go from, right, an alkyne a lot of times to an alkane. So each pi bond's like a chance to add something, right? So one step back is usually 1 pi bond back, and then another step back is the second pi bond. And then you add then one step back from that, the original step is adding the carbons. So if you see, like, right, because these are all we're doing addition reactions, right? So if you have an alkyne, you have 2 pi bonds, so you have 2 chances to add things. And if you have a terminal alkyne, you have H's to add carbons. But that's what you got to do first, right? You always will add the carbons first in the first part of the sequence, first part of the forward sequence. Going back each step, you're like going back and adding a pi bond each step backwards, right? If that makes sense. Because, right, for all of these, you're just adding stuff, right? All the stuff every single one of these reactions is addition reactions. We're just adding stuff. I guess we did the double elimination, but we did adding, all of them are additions except for this like deprotonation one. Those are the ones we've learned. So it's really, the sequence is usually you add the carbons, whatever you need to add, then you add something, use one of the pi bonds, and then use another pi bond to add something else. That's it.